April 7th. We're going to continue on Newton's second law. Yesterday we worked on page 64, the force diagrams, so you should be working on this in your Google Drive. So make sure you finish this worksheet. Speaking of worksheets, sometimes this is how I feel when we're talking about Google assignments, but generally you guys have actually been doing pretty good at submitting your stuff. Alright, so let's continue on the PowerPoint. So Newton's second law is all about unbalanced forces. So when you have an unbalanced force, the object is either speeding up or slowing down. And the rate that it speeds up or slows down depends on two things. The amount of force applied on it, so the bigger the force, the faster it will speed up, or the mass of the object, which means that the bigger the mass, the less quickly it will speed up. So it takes a lot more force in order to make it speed up and stuff like that. All right. So today we're going to do the simulations then, and the simulation is going to be talking about friction, because when we talked about unbalanced forces up till now, we've been ignoring friction. Friction is a force that slows things down or actually acts against the motion of an object. So in real life, there's actually friction, and there's actually four types of friction here. The first type of friction is static friction. That's what keeps things from moving in the first place. So when you have a box on a carpet, it's kind of hard to drag the box because the carpet will prevent it from moving. That's the friction force, the static friction. Velcro, that's a really good static friction, stuff like that. Once it's moving, then sliding friction. So it will make it harder to keep dragging. So it's easy to drag something, let's say, against ice because there's very little sliding friction. It's a lot harder to drag something through sand because all that sand particles will prevent it from sliding. When you're rolling, this is a little bit more complicated. When you're rolling with wheels, there's something called rolling friction. And then lastly, there's other friction just based on the molecules in the environment. So air resistance will slow something down. Water resistance will slow something down, and that's called fluid friction. So those are the four types of frictions. So here's a quick video from Fast 5.
Happen.
Of trouble moving the safe in the beginning because of static friction. However, once it started to move, because of the first law, it wants to keep moving, so you start getting this inertia and it makes it a little easier. There's still some sliding friction that is going to be slowing down the safe, but once it's moving, it's no longer has that static friction, so it's easier to keep going now that it's moving. So what happens if you don't have any friction? Well, the best example would be if you were on ice. And so here's a quick video about being on ice. Without friction, it's really hard because it's really hard to walk, it's really hard to move, and it's really hard to stop, stuff like that. So let's go to the simulation now. This is part 3 of the simulation of the friction. These are a little trickier because what it takes into account are two types of friction, the static friction and the sliding friction. And so you'll see that you need enough force to get it past the sliding friction. And that's what the first question is. How much force is required to get the child moving? But once it's moving, you need less force to keep it moving at the same rate. And so let's see how that works. So we have a child. So let's replace the box with a child. Let's add up all of our, let's show all of our values because that's always very useful. And then these buttons down here allow us to control. So at 50, it's a balanced force. The friction force is the same as the applied force. Okay, so let's go to 100. You'll notice that it's still balanced, right? No matter how much I push her at 100, the friction force, the static friction force, is going to keep her from moving. But once I go to 101, she starts to move. So that's the answer right there, is how much force do you need to get her to start to move. 100 was not enough, but 101 was enough. So in here, you would put 101 newtons. The second question is, once the child is moving, how much force is required to keep them moving at a constant speed? So once they're already moving, we have too much force because the sliding friction is only 75. So we need less than 101. So let's go back then. Let's go, no, that's not enough. I think, if you think about it, if the friction force is 75, then the applied force should also be 75, because now the sum of forces is 0. She doesn't speed up, she doesn't slow down, she's just moving. I hope her pants are pretty rugged right there. Okay, so that was the first one. Let's do the second one. So we needed 75 right here. The second one is how much force is required to get the trash can moving. So we go back, we replace it with the trash can. Okay, show all of our values. Right, let's see. 50 is not enough. 100 is not enough. 150 is not enough. And so right here, I'm going to just go one at a time until we can overcome the static friction. Oh, we might actually have to go a lot farther than that. All right. Let's see. There's going to be a magic number somewhere. Oh, looks like we got 200. So exciting. Oh, 251. All right, looks like 251 is the amount it takes to overcome static friction. So in your worksheet here, it would be 251. And then it asks for the second part. It asks, once it's moving, how much force is required to keep it moving? Well, you'll see that the sliding friction is 188, so that should be the answer right there. If we go back to 188, it should balance out, and there it goes. Once it balances out, you'll notice that it doesn't speed up or slow down anymore. So the answer there was 188. All right, so try the rest of the worksheet on your own. The friction ones, to try to do it with the mystery box to see how much is required to get it to overcome static friction, and then how much does it take to overcome the sliding friction, which is less, stuff like that.